in this week, we are going to learn about the most important and practically used distribution, which is the normal distribution. We begin by understanding about the probability density function or the PDF of the normal distribution, and then we will look at a very important rule which is referred to as the approximation rule or the empirical rule, and we will see how we can apply these rules to solve a few problems. Then we will go and listen, and this is where we are going to actually focus a lot on is what is the standard normal distribution and how do we use the normal probability tables, because we need to understand how to use the normal probability tables, and this is something which we are going to focus on for a lot of time. Then we will look at how we standardized or transform any normal variable to standard normal. This is called the standardizing the normal variable, and then we will spend some time in looking at the additive property of the normal distribution, and finally we will end it by looking at the percentiles of the normal distribution. So, this week we are going to pretty much, this is what is the agenda for this week. We start with the introduction. So, here we are going to introduce and study the normal distribution, which is by far the most important in all statistics, at least in a beginner's statistic course. You need to understand about this normal distribution both from a theoretical and application point of view. So, what is the PDF or the probability density function of a normal distribution? What is the probability density function of a normal distribution? So, as we know, the probability density function is given by f of x. So, I am looking at if x is a normal distribution, and as always I denote it as x is normally distributed. This is for a distribution. The parameters of this distribution are the expected value and the variance. So, I can say x is normally distributed with an expected value mu and variance sigma square. So, mu is the expected value or the mean, and sigma square is the variance. Some books and authors refer to this as mu and sigma. We are okay with either of these notations, but the way we read it is x is a random variable which is normally distributed. These are the parameters of the distribution. So, what is the density of this distribution? The probability density function determined by the two parameters, that is the expected value and the variance. So, my f of x is 1 by root 2 pi into sigma exponential e to the power of x minus mu by sigma whole square for x taking any real value. So, you can see that this normal distribution has two constants, one is e and other is pi. These are two very important mathematical constants. So, this x, the density function, is given by 1 by root 2 pi sigma e to the power of minus 1 by 2 x minus mu by 2 sigma square minus x is less than x is less than infinity. So, this density is defined for all real values of x. So, can x take a negative value? Yes, because I am allowing x to take a negative value. So, for all real values of x, this is the density of my random variable. So, what is the shape of a normal probability density function? So, if I am going to take for all the values of x, because x takes all values in the real line, I want to see what would be the shape of f of x, and I can see that the shape of this f of x is given by, if x is this and mu is the expected value or mean of my distribution, the shape of this curve is given by what I refer to as a bell shaped curve. So, you can see that the shape resembles a bell. You can see that it peaks at the value x equal to mean and it tapers off. It never goes below because it is a probability density function, but what I want you all to recognize is it does not touch the x axis, rather it is asymptotically, it goes parallel to the x axis. It is very close to 0, but it is not 0. So, this is a very key observation, its variability. So, this is the mean. So, you can see that the variance is measured by the standard deviation. Now, what is the height of this curve? So, if we all know that the density f of x, this plot, blue plot is that of the density, and I know that that is given by 1 by root 2 pi sigma e to the power minus 1 by 2 x minus mu by sigma whole square. So, at x equal to mu, this term becomes 0, 0 mu minus mu, which is a 0. So, e to the power of 0, which is a 1. So, at x equal to mu, my f of x is 1 by root 2 pi into sigma. Further, if sigma equal to 1, f of x equal to 1 by root 2 pi, and that I can see is point. So, for any value of mu, for x at x equal to mu, for any value of mu and sigma equal to 1, the height of the curve is 1 by root 2 pi. So, you can see that for mu equal to 2 and sigma equal to 1, the height. So, I at x equal to 2, so this is referred as the height is the, so the curve is at its peak at x equal to 2 and that is about 0.399. So, this is one for it is which is you can verify is 1 by root 2 pi. So, now let us look at what would happen for same mu, but a reduced sigma. So, for same mu, mu equal to 2, but sigma equal to half, I know that is going to be root 2 pi into 1 by 0.5. So, you can see that this is going to be twice 1 by root 2 pi, because again for at x equal to mu, I have the height which is defined. So, this would be e to the power of 0, which is equal to 1. So, twice of 1 by root 2 pi, which is going to be twice of 0.39, which is going to be 0.78 or close to 0.78, and I can see it is height is 0.79 when sigma equal to half. Again the height is the maximum at x equal to mu and the height is given by 0.798. So, in other words, what we observe is for the same mu. So, if I have the same mu, you can see that here I have plotted 3 normal distributions with the same mu. So, the first one, the blue is at x with normal mu and sigma equal to 0.5. My second x is the red x is a normal with mu is again equal to 2. All of them have the same mu, whereas sigma equal to 1. The third x is a normal with mu equal to 2 and sigma equal to 2. This is green, this is my red and this is my blue. I can see that the same mu. So, all the 3 curves have the highest at x equal to mu, but what we notice is as sigma increases, that is as my variability increases, I notice that my curve flattens. As my variability increases, my curve flattens, and since the area and since this f of x is a density function, the area under my f of x should always be equal to 1. It is a density function. In other words, minus infinity to infinity f of x should be equal to 1. That is the area under the density function. So, we notice that for the same mu and different sigma, I can plot as my sigma increases, the curve flattens. So, the larger the sigma, so as my curve increases, I notice that my curve flattens. However, if the mu, so here I have plotted for the same sigma equal to 1, same sigma, different mu. So, if you look at the blue is a x, which is a normal, again with mu equal to minus 2, and that is what we see here, sigma equal to 1. The red is mu equal to 0, the green is mu equal to 2. You can see that they are having the exact variability, but they are shifted. So, you can see that the blue and the red and the green have the same variability because sigma is same. So, the another property of the normal distribution is, you can see that when I am plotting x and f of x, and we also saw that this is my mean, and the mean it peaks. I also see it is symmetric about the mean. In other words, I can see that this curve which is shaded is actually, you can flip around the mu, you will find that this curve can overlap on this. In other words, whatever is here, it is symmetric around the mean. In other words, I can say that the probability that x is equally likely to be on either side of the mu because of symmetricity. That is, the chance of x lying less than mu, which is given by this shaded region. So, the chance of x lying lesser than mu is the same as the chance. So, this is going to give the chance of x lying lesser than mu, and I know that this is going to be equal to the chance of x lying greater than mu, and I know that since the area under this curve is equal to half, this area is equal to half, this area is equal to half, and these two areas are the same. Hence, we have probability x is less than or equal to mu is the same as probability x is greater than equal to mu, which is equal to half. This follows from the symmetric nature of the density function. Again, notice probability x is less than mu is the same as probability x is less than or equal to mu. Similarly, x is greater than mu is same as probability x is greater than equal to mu. Again, this follows from our discussion of continuous random variables. So, for any general mu and sigma, so if I am going to state that x is a normal variable with mean mu and variance sigma square, where any mu and sigma is given, we can see that x is always symmetric around its mean. So, I have my mean here, so I have a mean here, it is symmetric around the mean. Not only that, the shape is a bell shape. So, I observe that it is bell shape. It is centered at mu, so and it is symmetric around mu. This is again something I notice. Something which again I notice is the most of the observations lie between mu minus 3 sigma to mu plus 3 sigma. In the other words, that beyond the range mu minus 3 sigma and mu plus 3 sigma, it is very close to my horizontal axis. So, in summary, what we have learned so far is we introduced what was the PDF of a normal distribution, and we observed that the height of the curve is whatever 1 by root 2 pi sigma. For given a sigma, it is when x equal to mu, that is when I have the highest curve. One of the most important things to notice about a normal distribution is what we refer to as the approximation rule. We have seen that given x is a normal with mean mu and variance sigma square, I saw that a distribution, so when I am plotting my f of x, this is symmetric around the mu, it is bell shaped. What the approximation rule says is for any normal variable with mean mu and standard deviation sigma, there is the number or the area under the curve between mu minus sigma to mu plus sigma is going to be 0.68. Now, what does this 0.68 tell us? It tells us that 68% of my observations are within one standard deviation of the mean, because I know mu minus sigma to mu plus sigma is the interval which is within one standard deviation of the mean, because the standard deviation is sigma. So, the approximation rule says that within one standard deviation of the mean, I have 68% of the observations. Similarly, within two standard deviations of the mean, which is given by the yellow shaded region added to the blue shaded region, I have 95% of my observations which lie within two standard deviations. And what are within two standard deviations? It is mu minus 2 sigma to mu plus 2 sigma. So, I have mu minus 2 sigma here and mu plus 2 sigma, and I have 95% of my observations would lie in this interval. So, you can see between mu minus 3 sigma to mu plus 3 sigma, I have 99.7% of the observations lie here, and a very small percentage, that is 1 minus 0.997, which is 0.003 or less than 1% of my observations lie outside mu minus 3 sigma and mu plus 3 sigma. In other words, I can also specify based on the symmetricity that between mu minus, I know that between mu minus sigma to mu plus sigma, I have 0.68 or 68% of my observations that lie. So, again, this is the same as the number of observations that would lie here, or the proportion of observations which lie in this band is the same as, that is the band which I am going to mark in orange is going to be the same as the number of observations I am going to have in this green region. So, imagine I am shading this entire region green and this entire region orange. I am going to have the same proportion, and since it is symmetric, it is each one of them is going to be 0.34. In other words, I have between mu minus sigma to mu, I will have 0.34 proportion or probability. Between mu to mu plus sigma, I am going to have 0.34. Similarly, I know between mu minus 2 sigma to mu plus 2 sigma, I had a 0.95, which says that mu minus 2 sigma to mu, again by symmetricity, is going to be 0.95 by 2, which is going to be 0.475. Now, if this point mu minus 2 sigma to mu is going to be 0.75, mu minus 2 sigma to mu minus sigma is going to be 0.475 minus 0.340, which is going to be 0.135. So, I have that this area is 0.475 and this area is 0.34. Hence, this area, this yellow region is going to be 0.35. By symmetricity, I have this yellow region is also 0.135. Now, this region mu minus 3 sigma to mu plus 3 sigma, again I know is 0.997, that is what we have seen. So, the region is going to, so mu, so I can again continuing, I know mu minus 3 sigma to mu by my symmetricity is going to be 0.997 by 2. Now, which is going to be 0.4985, that is going to be this entire region is going to be 0.4985. From that I subtract this area. No, so if I subtract that area which is 0.475, I get the difference is 0.0235, which can be approximated by 0.0. So, if this is 0.499, if I approximate this by 0.499, this is going to be 0.024. Again by symmetricity, I know that this orange region, so the orange regions which I am going to have here, this orange region and this orange region is going to be 0.024. So, this approximate rule is a very powerful rule, and it helps us answer a lot of our probabilities even without actually computing them by looking at the approximation rule. Let us look at a few examples to answer that. So, the first example, it is given that a height of a certain population. So, when I am measuring height, so I know that I can look at a certain population, the height, that is I look at a population, it could be 1000 people, it could be 10,000 people, but what is the distribution of heights? I know that the mean is 69 inches and the standard deviation is 6.5 inches. This is what I observe. So, I want to know the proportion of the population whose height is less than 82 inches. This is what we need to understand. What I know is X is a normal with mean 69 and standard deviation 6.5. So, according to our approximation rule, what I notice is mu is 69, sigma is 6.5. So, let us write down mu minus 3 sigma, mu minus 2 sigma, mu plus, mu minus sigma, mu plus sigma, mu plus 2 sigma and mu plus 3 sigma. I have mu is 69, which is given here, and we can notice that this is my 69th point. Mu minus sigma is going to be 62.5. This is my mu minus sigma. Mu plus sigma is going to be 75.5. This is 62.5. Mu plus 2 sigma, which is 69 plus 13, which is going to be 82. Mu minus 2 sigma is 56. What I notice is mu plus 2 sigma is 82. Again, what is our question is X is less than 82, which is the shaded region. Now, the approximate rule tells me that the area between 56 and 82, which is the same as the area between mu minus 2 sigma to mu plus 2 sigma. Again, go back to the approximation rule that tells you that it is 0.95. This area is 0.95. between mu minus 3 sigma and mu plus 2 sigma is going to be, again you can go back to the approximation rule. You can see that mu minus 3 sigma to mu plus 2 sigma is 0.024. So, in effect I can see that this answer is going to be 0.95 plus a height is, so this is going to be above the mean. So, the area to the right of this is 0.024 or 25, hence the answer is point. So, I have a 0.95 plus a 0.025, which is a 0.975. I can solve it in another way also. I know that this blue shaded region is the same as 1 minus probability x is greater than 82, which is 1 minus the probability of the white shaded region. Again the white shaded region has a probability of 0.025 from the approximate rule. So, 1 minus 0.025 is 0.975. Hence, I get that the probability of x is less than 82. If I am approximating it by 0.024, it is going to be 976. So, it depends on what you are approximating it. If it is 0.024, it is 0.976. So, let us look at a few more examples. In this example, I have x which has mean mu equal to normal with mean mu equal to 15 and sigma equal to 4. So, I want to know what is the probability x is between 11 and 19. Very quickly we notice that 11 is 15 minus 4 and 19 is 15 plus 4. So, this the question we are asking is what is the chance x lies between 1 sigma of the mean, and you can know that again applying the approximate principle. I know 68% or 0.68 is the probability of mu minus sigma to mu plus sigma. They are very straightforward. Now, for the same thing, if I want to know what is the probability x is less than or equal to 23, I quickly realize 23 is 15 plus 8. So, which is the same as 15 plus 2 sigma. So, I am asking probability x is less than or equal to mu plus 2 sigma. There are two ways to do it. I can either find this, or I know what is this area. I know probability mu is greater than 2 sigma. That is something which I know is 0.025. So, that probability, so you can go back here. I know probability x is greater than 2 sigma. This is that probability which is approximation of 0.024 or 25 depending on what you are looking at, and it should all add up to 1. So, this I think with 0.0135. Okay, so this is all, again remember there are approximations. So, I can say that probability x is less than or equal to 23 is approximately 0.975. The probability x is less than or equal to 11. So, again 11 I recognize is 15 minus 4, which is mu minus sigma. So, x is less than or equal to 11. Again we know that this probability was 0.024. Now, again go back here, you can see that this probability between mu minus sigma to mu plus sigma was 0.135. So, I have 0.135 plus 0.024 or 25, which would make this probability 0.16. So, this shaded region will give me the probability 0.16. Again, I need to recognize that this is my mu, this is my mu minus sigma, this is my mu minus 2 sigma, this is mu minus my 3 sigma. And we are applying the approximation rule. Now, what is the probability x is greater than 27? I recognize 27 is 15 plus 3 into 12, which is mu plus 3 sigma, and I know that the chance that x lies greater than mu plus 3 sigma is approximately 0. The chance is very, very less. So, the probability x is greater than 27 is approximately equal to 0. So, now let us go and look at a few more applications of the approximation rule. In our earlier problems, we were given mu and sigma and we asked to compute probability x is less than or equal to x or some a. Now, suppose I am given the probability. Suppose I am given this probability. I want to know what is and suppose so given the probability and sigma, how do we compute mu? Let us look at a few examples to understand this. So, I am given here x is a normal random variable with I do not know the mu, but I know sigma equal to 3. I also know that the probability x is between 7 and 19 is 0.95. This is an information given to us. Now, if x is a normally distributed random variable with any mu and sigma, the approximation rule says that the chance that x mu minus 2 sigma to mu plus 2 sigma is 0.95. This is what our approximation rule says. What I have here is I do not know what is mu, but I know that this mu minus 2 sigma and this is mu plus 2 sigma. What is sigma? I know that mu minus 2 sigma is 7, mu plus 2 sigma is 19, sigma is 3. So, this tells me that mu is equal to 13 and I can verify that 13 plus 6 is 19. Hence, the approximate value of my mu is going to be 13. Okay. So, now let us look at another example of solving the same problem. X is again a normal random variable. Again, I do not know what is the mu, question mark, sigma equal to 3 here, and the information given to us is probability x is greater or equal to 16 or greater than 16, does not make, is 0.975. Again, what does our approximation rule tell us? So, it is telling that probability of x is greater than 16. So, I have 16 here, which is 0.975. Is asking what is your mu. So, I know x probability of x greater than mu minus 2 sigma equal to 0.75 because mu minus 3 sigma to mu plus 3 sigma I know as the value 0.025. So, because I know that the value of mu minus 3 sigma to mu minus 2 sigma takes the value 0.025. So, x greater than mu minus 2 sigma is 0.975. I know mu minus 2 sigma is 16 because probability x greater than 16 is 0.975. So, I equate these two. Mu equal to 16 plus 2 sigma, sigma is given to be 3 plus 2 into 3, which will tell me that the value of x or the value of the expected value of x is approximately 22. So, now we found what was mu given sigma and the probability. Now, can we do the same thing to find sigma given probability and mu? So, what we are given here is x is a normally distributed random variable with mu equal to 100, sigma is unknown, but the information that is given to me is probability x is greater than 130 equal to 0.025. What I realize quickly from the approximation rule is probability x is greater than mu plus 2 sigma is going to be 0.025. This is what I know from my approximation rule. So, I equate mu plus 2 sigma to be equal to my 130 because I am given probability x is 130 is 0.025. So, I equate these two. I know mu is 100, which gives me 2 sigma is 130 minus 100, which is 30, which gives me sigma is 15. So, the standard deviation is approximately 15. So, now suppose we apply the approximation rule now to compare two distributions. What do I mean by this? I am given x is a distribution which is normal with mean which is equal to 100 and standard deviation is equal to 2. Y is again another distribution with its mean equal to 105 and standard deviation equal to 10. The question that is asked is x or y more likely to exceed 105? In the other sense, I want to know if I am looking at x is greater than 105 and y is greater than 105, I want to know whether this is greater or this is greater, which is more likely. If this is the case, then y is more likely. If this is the case, then x is more likely. That is what we need to check. So, let us check what is probability of x and y greater than 105. Again, if we look at the curves, I have x is a mean with 100 and standard deviation 2, y is a mean with 105. So, the orange region which I have here gives this region gives us probability x is greater than 105 for the. So, this whereas the blue region gives me probability y is greater than 105. So, y is more likely to exceed 105. Similarly, I am asking the question, what is the chance, is x or y more likely to be less than 95? If you look at the orange region here, this gives the region x is less than 95, whereas the blue region gives y is less than 95. Hence, again y is more likely to be less than 95. Now, let us look at another example or application of the approximation rule. Again, you can see that we have just used the approximation rule given the fact that my random variable is a normal random variable. So, the scores in a particular aptitude test is again normal with mean mu equal to 400, standard deviation. So, this is my mu, this is my mu plus sigma, this is my mu minus sigma, standard deviation is 100. This is going to be mu plus 2 sigma, this would be mu minus 2 sigma, this is going to be mu plus 3 sigma and this is going to be mu minus 3 sigma. Again, my approximation rule says that 34% would be here, 34% would be here. This is going to be 13.5 or 135, this is 13.5 and this is going to be 0.002.4 which is very, very less, or 0.0024 or 2.4. 2.5. So, you can see that the top 5%, the top 5%, so should it consider people whose score are 400? 400 if I take as a threshold and I put that as my, so I can see that people greater than 400 are my top 50% and not my top 5%. So, this is a no. Similarly, 450 would also be greater than my this percentage, 450 is also going to be no. Greater than 500 is going to be 13.5 plus here 2.4, about 15%. Again this is no, whereas greater than 600 I know is a very small or 2.4. So, what is the consider applicant scoring in the top 45? It would consider people whose score is greater than 600 marks. So, in this section what we have learnt is the approximation rule and its application to compute probability given the expectation and standard deviation and to compute the mean given the probability and standard deviation, and to compute the standard deviation given the probability and the mean.